Welcome back to the 10th online module for ManEc Fin 453. Today we're going to be executing portfolio optimization. In essence, we're going to be putting in practice the things that we learned on a theoretical level in Excel module number 9. So we can find ourselves on the map here and we can see that this is the second to the last Excel module for the semester. After this one, the last one will be mapping out the efficient frontier and the capital allocation line. As far as our Excel training and review objectives, you can see that we've covered almost everything on here. Today what we want to do are array and matrix functions as we try to execute portfolio optimization. So that is our sole and singular goal for today, is mean variance portfolio optimization for a 7-asset portfolio. I'm going to be demonstrating the principles to you using only 4 assets. You'll execute it using 7 assets. Now, what we mean by mean variance portfolio optimization is either maximizing the return or minimizing the standard deviation of a portfolio, or perhaps maximizing the ratio of return to standard deviation. Well, in order to do that, you have to understand how to calculate expected return and standard deviation for a portfolio. I tried to make the argument in the previous Excel module that once your portfolio exceeds 3 assets, trying to calculate portfolio expected return and especially standard deviation becomes very unwieldy. And the only way to make it truly tractable and simple is to use matrix algebra. So remember, what you have to do is define 2 vectors and a matrix. The first vector is the weight vector. So if you have k assets in your portfolio, and you will have 7, I will have 4. But if you have 7 assets, then you would have a 7 by 1 vector of the weights that each of the individual assets comprise your portfolio. We just call that the W vector, the weight vector. The next vector is the expected returns, or the mu vector. And this is also going to be a k by 1 vector, so you would have 7 by 1 vector that contains the expected returns of the individual assets in your portfolio. The sigma matrix is a little bit more complicated. This is the variance covariance matrix of the assets, so it would be k by k. So you would have a 7 by 7 matrix with the variances on the diagonal and the covariances on the off diagonal. Once you define the W vector, the mu vector, and the sigma matrix, it's relatively straightforward to determine the expected return and the portfolio standard deviation. Expected return is simply W transpose mu. And the portfolio standard deviation is simply the square root of W transpose sigma W. So our primary objective today is going to be simply to create the variance covariance matrix and find the portfolio expected return and portfolio standard deviation using matrix algebra in Excel. Once you find portfolio expected return and standard deviation, then there are 3 different ways you can optimize the portfolio. First off, you can maximize the portfolio's expected return given a set level of acceptable dispersion or volatility. The second way is you can minimize the portfolio's dispersion or volatility given a set level of desired expected return, or related to that, you can just absolutely minimize the variance of the portfolio. Lastly is you can maximize the ratio of the expected return to the variance of the portfolio. In other words, maximize the Sharpe ratio. Well, in order to figure out the portfolio standard deviation, you need the sigma matrix, which is the variance covariance matrix. Remember, we talked about how to get the variance covariance matrix. The easiest way to do this is to construct an n by k matrix, where n represents the number of months of observations, k represents the number of assets. So you're going to do 60 months or maybe longer. So you're going to have 60 months or 66 months perhaps of data, so that's the number of rows, and you're going to have 7 assets. So you'll have 66 rows and you'll have 7 columns. But remember, you're going to have 66 rows of prices, which means you'll only have 65 rows worth of returns, because in the first month you wouldn't be able to calculate the return. So you're probably going to have a 65 by 7 matrix of monthly returns. The next step is to calculate the average return for each asset, and then for every single monthly return observation, subtract out the average return for that specific asset. that's going to leave you with a matrix that is, again, n by k, or in your case it'll be 65 by 7. We're going to define that new matrix, which represents the monthly returns minus the averages. We're going to define that as the excess return matrix, and I'm going to call it X. Once you have that, calculating the variance covariance matrix is pretty straightforward. You simply take X transpose, multiply it by X, and then divide every element in that matrix by the number of return observations, which for you will probably be 65. So the deliverables on the assignment is going to be an Excel file in which you have a portfolio consisting of 7 assets, which I'll outline below, and you're going to optimize the portfolio in 3 ways. You're going to show me the minimum variance, you're going to show me the maximum return with the variance set to the lowest of the individual assets, and you're also going to show me the maximum Sharpe ratio. You're going to use monthly data over the period 6/30/2007 to 12/31/2012. Your assets will be SPY, VWO, EFA, AGG, TLT, MUB, and GLD. This is the S&P 500 ETF. This is an emerging markets equity ETF. This is Europe, Australia, and Far East developed companies equity ETF. This is a corporate U.S. bond ETF. This is U.S. Treasury ETF, U.S. municipal bond ETF, and this is a gold ETF. Now, that's certainly not an exhaustive list of all the asset classes. Probably would want to include some real estate, probably would want to include some foreign sovereign debt, some foreign corporate bonds, maybe some high yield bonds in America. So we're leaving out a lot of asset classes, but it will at least be illustrative, I think. So I want to demonstrate to you how to do this with just 4 assets. So I'm going to be using 4 out of the 7. Here's the 7 you're going to use. Here's the 4 that I've picked. So I'm going to use S&P 500. I'm going to use the U.S. corporate bond ETF, the gold ETF, and the U.S. Treasury ETF. So this is the macro that we picked up in the first Excel assignment. All I'm going to do is go and view the macros. I'm going to run this Get Yahoo Finance macro down here, and that's going to pull in monthly data for each of my 4 ETFs. Now, first thing we want to do is just calculate the returns for those. So let's go ahead and do TLT. And what you actually can do is this. You can highlight all 4 tabs. And then we're just going to take the natural log of the ratio of this month divided by previous month. Send that all the way down. Format it as a %. And then click off of the tab. And you should see that for each of your 4 tabs, you've just calculated returns. So the only thing you really need to do is label it then. Now what we need to do is we need to aggregate all this data. We need to get an N by K matrix of returns. So let's go ahead and get another tab here. We'll call this our returns tab. And we just want the date. So let's go and get the first date, which would be right there. And we're going to take that down 65 months, and you'll see why. Because if you go and look at our data set, in the first month we don't have any returns because it takes 2 months to get returns. So that's why we're only going to have 65 months, right? We have date in row 1, and then we have 65 months worth of returns. So we just want to get the data for each of our 4 assets. We just want to aggregate those returns. So just go and grab TLT, grab its return, pull it in. And I'm going to do the same for all 4 assets. I don't think you need to watch me do that. So let me do it real quickly here. Okay, so what I've done is I've aggregated all of the returns data. Here is my N by K matrix. N meaning 65 months by 4 assets. So I have 4 columns, 65 rows. This is our N by K matrix. What we need to do, though, is for every single observation, we need to subtract out the average return to that asset. So all of these need to have the average return for TLT subtracted out. All of these need to have the average return for GLD subtracted out. So we need to calculate the average return. So let's just go to the bottom here, and let's calculate the mean and the standard deviation for each of these. So we'll just calculate the average like so, and we'll also calculate the standard deviation. And I want to do standard deviation of a population, and I'll try to explain why here in a second. So we're just calculating standard deviation of a population, giving it some formatting. Now what we need to do is, for every single monthly return up here, we need to subtract out the average return for the specific asset. So I'm going to do this right next to it. So right here I'm going to take the return to TLT and subtract out the average for TLT. What you want to do is lock in that row number. If you do that, you should be able to slide this across and shoot it down as well. Hopefully everybody can see why. If you lock in the 68, then as we slide across, it becomes C2 minus C68, which is perfect, D2 minus D68. But as we drop down, it's going to become B3 minus B68, which is exactly what we want. So by locking it in, we get what we want. Now this right here represents our excess matrix. That's the excess return matrix. That is the X matrix right here that we're going to need to calculate the variance covariance matrix. So in order to get the variance covariance matrix, we need X transpose X, and then we need to divide all the elements by the number of returns that we have. Let's create a new tab. We'll call it the variance covariance tab. And remember, it's going to end up being a 4x4 matrix. So there's our 4x4 matrix. And what we're going to do is we're going to do matrix multiply, and we're going to get the transpose of that excess matrix. So we come up here and transpose it. So instead of being an n by k matrix, that turns it into a k by k matrix. We multiply that again by the same exact matrix, the X matrix. So we're taking X transpose X, and then we want to divide that by however many monthly returns we have. So I'm just going to count how many monthly returns we have for this first asset. Now, since we have a matrix multiplication formula right here, M multiply, since we have that matrix multiplication formula, you have to hit Control, Shift, and Enter as you execute the function. That right there should be our variance covariance matrix. We can put some labels on it to make it a little bit more readable. Now, I didn't show you how to do this because it's not necessary. You don't need to do the next step, but I like to do the next step just to give myself peace of mind. What I want to do is I want to transform the covariance matrix, the variance covariance matrix, into the correlation matrix. Now again, it's not necessary, but by doing this, I'll be able to know if I made a mistake. Because when you turn this into a correlation matrix, you should get a very specific result on the diagonals. What's the specific result you should get on the diagonals? Well, the correlation of TLT with TLT is 1. The correlation of GLD with GLD is 1. So the reason I'm going to transform this into the correlation matrix is it'll tell me if I made a mistake. If I get something other than 1s on the diagonals, that means I messed up somewhere. Well, in order to do this, it's not terribly hard. All you do is go and highlight the entire variance covariance matrix, and then you divide it by a matrix that you have to create by doing matrix multiplication around the standard deviation. So what you do is you transpose the standard deviation vector and multiply that by itself. If you do that and you hit Control Shift Enter, because again we have a matrix multiplication function, so since we have a matrix multiplication function, hit Control Shift Enter. If we've done it correctly, then this should spit out the correlation matrix. So you kind of keep your fingers crossed as you do this. And you can see that in fact we've done it right because we've got 1s on the diagonals. So the fact that we're getting 1s on the diagonals tells me that we did it correctly, but also I'm seeing that there's some really low correlations among these assets. There's even some negative correlations. So I want you to think right now, what does that mean? We're starting to construct a portfolio with assets that have low correlations. When you construct portfolios of assets that have really low correlations, there should be some really strong benefits from diversification. So that's our task now. We want to start to combine these in portfolios. So let's go ahead and create a new tab. And we'll just call this our optimization tab. And I'm going to start here just by noting the ticker symbols. We have TLT, GLD, AGG, and SPY. What we're going to do is we're going to get their expected returns. Now, by the way, when you type in E parent R parent, it's going to do that. Just hit Control Z and it'll turn it back. So let's get the expected returns, let's get the standard deviations, and let's also calculate the Sharpe ratios. So in order to do this, I'm just going to highlight all 4 cells, hit equal, and then I'm just going to transpose these average returns that we calculated earlier. Close the parents, Control Shift Enter, and they'll show up right there. We just format them a little bit, and we get it to look like so. We'll do the same thing with standard deviation, so we'll highlight the 4 cells, and we'll just go and transpose that standard deviation vector that we calculated before, and just copy and paste the formatting, and there's our standard deviation. Sharpe ratio is just expected return over standard deviation. We don't usually present that as a decimal, or as a percentage. We usually present it as a decimal, like so. And there you have it. Now what I want to do is I want to start putting together portfolios. So let's get the total portfolio weight, and you'll see what I'm doing here in just a second. So let's do this. Let's create portfolio weights, and why don't we start off with an equally weighted portfolio. And so those are just going to add up to our total portfolio weight. And what we want to do is calculate portfolio expected return, portfolio standard deviation. Let's annualize that as well. So annualized expected return and annualized standard deviation. And then let's get the Sharpe ratio as well. And we will align those to the right. All right, this is where our matrix algebra comes in. Remember, in order to get portfolio expected return, we need the weight vector transposed times the expected return vector. So there's our weight vector. We're going to transpose it. We're going to multiply it by our expected return vector. So here we go. Matrix multiplication. Transpose the weight vector. Multiply it by the expected return vector. And lock that in, because we're going to slide these formulas across at some point. And remember, Control Shift Enter. Give it a percent, and give it a little bit of formatting TLC. To get portfolio standard deviation, we have to do W transpose sigma W and take the square root. Please note that in Excel, you can only matrix multiply 2 matrices or vectors. So we're going to have to do 2 matrix multiplications. So let's do M mult, M mult. And the first one that we'll do is the first part. So we'll transpose the weight vector, and we'll multiply that by the variance covariance matrix and go ahead and lock in the variance covariance matrix. Well, that creates a vector. If you multiply W transpose against the variance covariance matrix, that creates a vector, and we're going to multiply that back against the weight vector. So what we're saying right here is, first off, do W transpose sigma, and then multiply it by W. But remember, we need the square root of that. Don't forget that. That will mess you up if you forget it. And Control Shift Enter. And then just give it some formatting TLC like so. Now let's annualize our expected return. So multiply that by 12. And let's annualize the standard deviation. So we multiply the monthly standard deviation by the square root of 12. And let's go ahead and calculate the Sharpe ratio, which is the annualized expected return divided by the standard deviation, presented as a decimal. And there we have it. Now, what we want to do is we want to start optimizing this portfolio. And the first thing we want to do is minimize the variance of the portfolio. Now, what you should be able to do is copy all of those formulas across. But what we're going to do is change the weights. So we're going to come into the Data tab and grab the solver. And what we want to do is we want to optimize our portfolio standard deviation. Specifically, we want to minimize it by changing the weights in our portfolio, subject to this constraint. our total portfolio weights have to equal 1. Now, there's one other constraint you have to think about, and it's this. Do you want to allow short selling? If you want to allow short selling, you need to unclick this button, because right here this option says make unconstrained variables non-negative. So we haven't constrained any of the weights. We haven't constrained the individual weights. If you leave that checked, it won't let them go negative. Negative percentages in your portfolio would represent short selling. So if we solve it like this, that would be not allowing short selling. So there's the result if we don't allow short selling. Now, what if we allow short selling? You simply go back in and uncheck that box, resolve it, and now you get a really interesting outcome. It tells you that what you should do is short sell quite a bit. You should short sell the Treasury ETF, the Gold ETF, and the SPY ETF, this S&P 500, and invest all of it into the corporate bond ETF. And if you do that using historical data over the last 5.5 years, then you would get a portfolio standard deviation of 0.992% per month. Now, this is really, really important, because the primary benefit of diversification is it can allow you to minimize risk. Please notice that the lowest monthly standard deviation of any of the individual assets is 1.25%. Through diversification, the power of diversification is this. We can combine these 4 assets that have the lowest single standard deviation of 1.25, and because of the covariances, we can arrive at a portfolio that has a standard deviation that's lower than any one of the individual single assets. That's very powerful. You can also see that the resulting portfolio has a Sharpe ratio that exceeds any of the individual Sharpe ratios. So that's the first way that we want to optimize this portfolio. The second way we want to optimize it is to maximize the return subject to one more constraint. So let's do this. Let's copy and paste across. Let's bring back up the solver function. But now we want to set our objective function. So the output that we want to alter is the portfolio expected return, and we want to maximize it by changing the weights in the H column subject to the constraint that H8 equals 1, but we want to add one more. We're going to make it so that our portfolio standard deviation can go no higher than the standard deviation of the lowest, least volatile individual asset, which is the bond portfolio right there, the bond ETF. So what we're trying to do is create the highest return we can get in our portfolio while keeping our standard deviation at the lowest level of any of the individual assets. So I forgot to actually put the constraint in. So we're going to make it so that, we're going to make it so that our portfolio standard deviation is less than or equal to that 1.25%. So let's look at what we got going on here. What we're going to do is we're going to maximize the return by changing the weights, ensuring that the weights equal 1 collectively, and also ensuring that the standard deviation of our portfolio is less than or equal to 1.25%. Why don't we constrain it so that there's no short selling first? And there's the outcome that we get. And now let's go back in and resolve it while allowing for short selling. And there's the outcome. So this is quite interesting. What it's saying is we should short sell TLT, which is the Treasury. We should short sell the S&P 500. We should put a little bit in the GLD ETF and a lot in the corporate bond ETF. If we do that, you can see we get a portfolio standard deviation quite a bit low. Well, actually, it's almost exactly equal to the standard deviation of the AGG ETF. But what's neat about that is we get a monthly expected return that's 5.6 basis points higher. So in other words, we've created a portfolio with a lower standard deviation than the lowest volatility asset in our portfolio, but we're getting an expected return that's noticeably higher than the expected return on that individual asset. Again, just demonstrating the power of diversification inside of a portfolio. All right, the next thing we want to do is we want to max out the Sharpe ratio. So again, we can copy and paste all this over. Go back into the solver function. Now we're going to set the objective function as our Sharpe ratio. We're going to maximize it by changing these variables, the weights. We're going to get rid of the standard deviation constraint. We have to change the total portfolio constraint so that instead of H8 equals 1, it needs to be I8 equals 1. And I'm just going to go ahead and leave it unconstrained, meaning we're going to allow for short selling, and we're going to solve it and see what we get. You can see that the maximum Sharpe ratio we can create would be by short selling TLT 17.65%, short selling SPY by 7.68%, investing 3% in GLD and 122.27% in AGG. If we do that, we get a monthly expected return of 0.497% and a monthly standard deviation of 1.086%. We get a Sharpe ratio of 1.59, which far eclipses the Sharpe ratio of any of the individual assets. So in essence, we've incredibly deflated the risk while keeping our expected return about even with AGG, which gets us a really high Sharpe ratio. On an annual basis, you'd be creating a portfolio that should get an expected return of about 5.969% and an annualized Sharpe ratio of 3.761%. So what I want to do at this point is we're essentially done with the assignment. I just want to doctor up the formatting a little bit. I don't think you need to watch me do that, so I'm going to step away for just a second, format it, and then we're going to come back together and make one really important observation about all of this. All right. So all I did is I applied some formatting to it to make it a little bit clearer for us. And sorry, I just can't leave it alone, can I? Anyways, I've applied a little bit of formatting for us just to make it a little bit more readable. And I want you to see that this is really, really cool, right? I mean, you have these individual assets. The lowest standard deviation you can get from the individual assets is 1.25%. We were able to create a portfolio that had a monthly standard deviation of less than 1%. Here's the Sharpe ratios for the individual assets. We were able to create a portfolio that absolutely blew that out of the water. So you're seeing very clearly the power of optimization and diversification. But there's one massive caveat or warning that you need to understand, and I hope to high heaven you did not turn off this module before you got to this point. All of this analysis is based on a massive assumption. It's based on the assumption that what happened in the past reliably predicts the future. It's based on the assumption that the expected returns we've seen over the past, so the realized returns over the last 5.5 years, are going to continue into the future. It's based on the assumption that the standard deviations over the past 5.5 years are going to continue into the future. And it's based on the assumption that these correlations that have happened over the last 5.5 years are going to continue into the future. But you have to ask yourself, do you really believe that? Do you believe that treasuries are going to earn an average of 82 basis points per month? Do you believe gold is going to earn an average return of 1.39% per month? Well, my head tells me absolutely not. Now, I might trust these correlations. I believe that correlations over a period of 5.5 years, even if it was an unusual period of time, I believe that correlations over 5.5 years probably are pretty reliable. So I'm probably okay with my variance-covariance matrix. And maybe I'm okay with the standard deviations, but I'm totally uncomfortable with the expected returns. And you need to understand that everything you did over here is based on that assumption. Well, what if that doesn't hold? What if we really don't believe that gold is going to have a 1.39% expected return? And what if we don't believe that AGG is going to have a standard deviation of 1.25%? Well, this is where the science of finance runs headlong into the art of finance. You would need to come in and judgmentally change these things. You would need to judgmentally come in and say, well, we don't buy these numbers, so we're going to change it. And you try to make it what you think it's going to be rolling forward. So you and your team of analysts would come in here and make whatever changes you think are necessary to the past data so that it accurately reflects what you think will happen in the future. And then you execute the analysis But even at that point, you realize that you've had to make a lot of assumptions in order to execute the analysis. So look, this is really cool. This is super high-level stuff for undergraduates to be doing. If you've followed me to this point, you ought to pat yourselves on the back. We've got one more step to go. We're going to take this and create the efficient frontier and the capital allocation line. And from there, you'll be able to apply modern portfolio theory, which says all I have to do is map out the capital allocation line, pick my standard deviation, and I'll know exactly what kind of portfolio I should set up. So that's where we're headed. If you have any questions, you can contact me or the TAs, and we certainly wish you the best of luck as you try to execute this.